this is Math 105, section 1.6. We're going to look at application problems in this section, and we'll just deal with specific examples, not all of the types of problems in this, but I'll explain that in class. So we'll start with guidelines for how we model with equations, how we're solving story problems. So our first step is to identify the variable. Okay, identify the quantity the problem asks you to find. Read the question carefully. So careful reading the question, and then introduce notation. Okay, so make sure you read the problem a few times so we really understand what's going on, and we can call our variable x or some other letter. Okay. Second step is to translate that word problem into algebra. So translate from words to algebra. Okay, so read each sentence in the problem again and express all the quantities in terms of the variable. Okay. Draw a diagram or make a table. So that's important that we're doing some sort of diagram or some sort of table to make that translation. And this is where most of our work is in these two sections, the first two steps there. So step 1 and step 2, identifying the variable, reading the problem, make sure you really understand it, and then translating to algebra. Okay. And then the third step is to set up the model. This is where we're actually using the equation. So set up the model. Okay. Give a relationship between the expressions in step 2. Okay. And set up an equation or a model that expresses this relationship. So this is where we actually get our math problem, our mathematical model. Okay, and our last step is pretty straightforward. We're just solving the equation and check your answer. And then express your answer in a sentence that answers the question posed in the problem. So we kind of translate back. We answer our problem, and then we solve our equation and we answer our problem that was originally posed in words. Okay. So the first example we'll look at is you're renting a car, and the car rental company charges $30 a day and 15 cents a mile. Okay, and Helen wants to rent her car for 2 days, and her bill comes to 108. And we want to know how many miles did she drive. Okay, so let's identify x as the number of miles driven. That's our unknown, and we're going to translate this from words into our language of math, or in this case, algebra. Okay, so x is the number of miles driven, which we don't know. The mileage cost is 15 cents per mile, so we're going to put 0.15, which would be dollars, right, times x. So every time we go a mile, we pay an extra $0.15 or 15 cents. Okay, and then the fixed daily cost is $30 per day, so it's 2 times 30. So this is what our model looks like. We have that fixed daily cost of 2 times 30, or $60, plus 0.15 times x, which is 15 cents for every mile we drive, and then our total cost would be 108. And so what we're going to do is solve for x there, and that will tell us how many miles gave us that cost. Okay, so we get x by itself. We have 0.15x, and we divide both sides by 0.15, and we get x equals 320. Okay, from that original equation. So that's how we would answer our question, that Helen drove her rental car 320 miles. And just to check our answer, the total cost would be 0.15 times 320 miles plus 2 times 30. That's our daily cost, fixed daily cost. And we add that up, we get 108. So we can see that our answer is correct. Okay, the next type of example we're going to look at is a geometric problem. And here's our problem. We have a square garden with a walkway that's 3 feet wide around its outer edge. Okay, and this is our figure here. Okay, you can see that walkway is green. Okay, if the area of the entire garden, including the walkway, is 18,000 square feet, that should be a foot squared. What are the dimensions of the planted area? Okay, so this is our planted area, is the inner part, and we can see x is one side of the planted area, right? And then we can see that it's 3 feet around on each side. Okay, so we'll start by identifying a variable x as the length of the planted area, the length of the inner garden. Okay, and then translate from words to algebra. Okay, so the length of the planted area is x. And the length of the entire garden is x plus 6, because we're going to add 3 feet on each side, because it goes all the way around, right? So the length of the whole thing would be x plus 6. Okay, and then the area of the entire garden is x plus 6 squared. So this is a square that we're looking at. Okay, so we say that the area of the entire garden, including the walkway, is 18,000 feet squared. That was given. So one side is x plus 6, and if we square it, because it's a square, we get 18,000. So x plus 6 squared equals 18,000. We take the square root of both sides. We're not going to do plus or minus because we're talking about a positive dimension, so we wouldn't worry about the minus. So we have x plus 6 equals square root of 18,000, and then we subtract 6 on both sides to get x. So x is just the square root of 18,000 minus 6. So the square root of 18,000 minus 6 is x equals 128. So the plan of the garden is about 128 feet by 128 feet as a perfect square. Okay, let's look at another geometric problem. We have a rectangular building lot that's 8 feet longer than it is wide, and it has an area of 29,000 square feet. And we want to find the dimensions of the lot. Okay, so the first thing we're going to do is identify the variable. So we want to find the length and the width of the lot. So we'll start with W equals the width, okay? And if the length is 8 feet longer, then L would be, let's write that in here, L, I'll just use that for L, is W plus 8. So we don't really need two variables there. We can always use W plus 8 for L. Okay, so here's the width of the lot, which is W. The length of the lot is W plus 8 because it's 8 longer than the width. Okay. And remember, area of a rectangle is width times length, so W times L is going to be 2,900 square feet. But we know that L is W plus 8, so we can just substitute it right away. We don't need to use L at all, really. So W times W plus 8 is 2,900. Now if we distribute on the W plus 8, we get W squared plus 8W equals 2,900. That's a quadratic equation because we have a square on the W there. So remember, with quadratics, we want to get 0 on one side and try to factor this. Okay. And in fact, we can factor this. W minus 50 times W plus 58 equals 0. This is the factorization of that quadratic. So we get two solutions, W equals 50 or W equals minus 58. Now we can throw this one out because it's negative. So we would stick with the positive one here because we're talking about dimensions of a rectangle, right? So our width is 50 feet, and then their length would just be W plus 8, which is 50 plus 8, or 58 feet. And you can see it kind of comes up here as a solution, even though it's negative. So use the positive because we're talking about dimensions of a rectangle. Okay, and then you'll get the 58 when you add 8 to get the length. Okay. Now it may not be obvious that we can factor this, and that does require a bit of trial and error, at least a little bit of intuition. But if you have trouble factoring this, we can always use quadratic formula here too. Okay, with a calculator. Okay, the next type of problem we're going to look at is called a work problem, and this is where we're trying to see how long it takes two people or two entities to do a task at the same time. So here's an example. We have this reservoir that we need to lower by 1 foot. Okay, so it's a big tank of water. Okay, and we have these two drains or these two spillways that we can open. And if we open one of them, it lowers that by 1 foot in 4 hours. So if we just open spillway A, it takes 4 hours to go down 1 foot. Okay, and if we open the smaller one, there's a smaller drain called spillway B, it takes 6 hours to lower. Now that's just if we open each one individually. So 4 hours for spillway A, 6 hours for spillway B, and we're trying to get the water to drain out so the level goes down by 1 foot. Now the question is, how long will it take to lower the level by 1 foot if both spillways are open? In other words, they're both draining at the same time. Okay. So first step is to identify the variables. So we're going to say X is how long it takes to lower the water level by 1 foot if both spillways are open. Okay. Now we can't just say it's 4 plus 6, and we can't just say it's the average of 4 and 6 either. Okay. We have to think about this a little bit. If it takes 4 hours for one drain, the faster one, then if you add the second drain, it's not going to take more than 4 hours. It's going to take less, right? Because the other drain is kind of contributing to lower that water level. So if one takes 4 by itself and one takes 6 by itself, then together it's going to take less than 4. Okay, so it's not the average. That's kind of intuitively you might think that, but that's not true. Okay, so instead we look at the fraction of the job that can be done in 1 hour by each spillway. Okay, so and we're going to use X here. So time together is our unknown. Okay, but look at A. A takes 4 hours. So in 1 hour, it lowers it by 1/4 foot. And then B, because it takes 6 hours, it lowers it by 1/6 of a foot in 1 hour. Okay, so together, we would say in 1 hour it lowers it 1/4 plus 1/6. And what we do is we keep adding those up hour by hour till we get to 1. Okay, or we can say this: the distance A and B together lowers the level in 1 hour is 1 over x feet. So we can think of x as like the fastest rate because it's A and B together. So it's going to lower it by 1 over x feet in 1 hour if both of them are open. Okay. Now x is going to be something less than 4, so we can think of it that way. Okay, so basically this relationship, the fraction done by A plus the fraction done by B, now this is for 1 hour, equals the fraction done by both together. Okay, so we can say 1/4 plus 1/6 equals 1 over x. Now to solve this, we're going to multiply both sides by 12x. Okay, and the reason for that is because we have denominators of 4, 6, and x. Okay, that would be our least common multiple of these three. Okay, so when we do that, we get 3x because we take 12x divided by 4. Okay, and then we get 2x because 12x divided by 6 is 2x, and then equals 12. 12x divided by x is 12. Okay, that just gives us 5x equals 12. Okay, and we just divide both sides by 5, and we get x equals 12/5, which is 2 2/5, so it's 2.4 hours, 2 hours 24 minutes to lower by both by 1 foot. Okay, and here's an alternative way to look at this problem. Think about, when they're what each part is contributing. So if R1 spillway A does 1/4 of the job, lowering, what we're trying to do is lower it by 1 foot. So that we'll just say that's our job, is try to lower the thing by 1 foot. So after an hour, spillway A does 1/4 of that. Spillway B does 1/6 of that. Okay, and they're doing it together, so we're going to add those two parts. After 2 hours, spillway A does 2/4, and spillway B does 2/6, and we add those up together. Okay, and then after hour 3, spillway A has done 3/4 of that job, and spillway B has done 3/6 of that job. Now we're going to keep adding these fractions using our time until we get to 1. Okay, so we're saying after t hours that we're going to have t over 4 plus t over 6, and we want it to be 1. Now that 1 means that the job is completed. Okay, so we're just looking at any job. It doesn't matter what the distance is, just that we're completing this job, and it takes 4 hours to do this, for this one to do it, and 6 hours for this one to do it. We're adding those parts together. So this is our relationship. We have t over 4 plus t over 6 equals 1, and this is kind of our general thing. Time for A solo, this would be our 4. B would be our time for B solo, that would be our 6. And we could say, now we're using x because we used x up here, but that would be our t here. Okay, so x over 4 or t over 4 plus x over 6 or t over 6 equals 1. So there's our relationship. And it's the same. We would still get that x equals 12/5 if we did this problem, where the 4 goes here and the 6 goes here. So this is another way of looking at that. But, gets the same solution. Okay, now we're going to look at distance problems. So remember our common distance formula is that distance equals rate times time, okay, where rate is either the constant speed or average speed of a moving object. So for example, if you're going 60 miles per hour, that would be our rate. For 4 hours, that would be our time. Okay, we're going to multiply that rate times time to get distance. So 60 miles per hour times 4 hours is 240 miles. Okay, so D equals R times T is another way to write that, and usually that's easy to remember. That is just dirt. D equals R times T. Okay. Okay, so let's look at this example. A jet flew from New York to LA, which is a distance of 4,200 kilometers. The speed for the return trip, going from LA to New York back, was 100 kilometers per hour faster than the outbound speed. Okay, so trip back was faster, so the trip out was slower, trip back was faster. Okay. The total trip back and forth took 13 hours, and we want to know the jet speed on the way out. Okay, which is the faster speed. Okay, so, or sorry, the slower speed. So S is the speed from New York to Los Angeles. That will be our unknown. Okay, and then the speed from LA to New York coming back is S plus 100. It went faster on the way back. So we'll set that up as our variables. Okay, actually one variable, right? And this is where it's important, or a good idea that we write a table, okay, when we're translating from words to algebra. So we're going to show both trips, okay, New York to LA, the outbound, and then the return, LA, New York, and we're going to do distance, rate, and time, and we're going to show them separately in a table. Now notice the distance is the same for each one because it took the same path, we'll assume. We have the two speeds, okay, so S on the way out, S plus 100, faster on the way back. And time is, now we actually did a calculation for this, but we took our D equals R times T, and we divided both sides by R, so we got T time equals distance over rate. Okay, so that's how we're finding this thing. We're taking distance divided by rate, distance divided by rate to get the time for each one, because the times are going to be different, right? Okay, so we have this table set up. So it's very important that we make a table so we can organize our information and put, distance, rate, and time for each one. Okay, so we've got, remember, time equals distance over rate. That's how we got that from the previous table. And we're going to take the time outbound plus the time returning to get our total time. Remember, our total time was 13 hours. So T1 plus T2 equals 13. So this is our equation. Okay, distance over rate for the way out, distance over rate for the way back. Time 1 plus time 2 is 13. Okay, now we're going to have to multiply both sides by, if you think about this being factored, right, we're trying to find our lowest common denominator. So this is a factor and this is a factor. Okay, so we're going to have to multiply these two to get our common denominator, this S, and this S plus 100. So we multiply both sides of this times S plus 100. So this is what we're doing here. We're going to take this whole side and multiply it times S plus 100. And then we do the same thing to the other side. Okay. Now the reason we do that is because we want to cancel out these denominators here. So this S times S plus 100 will cancel the S here, and it'll cancel the S plus 100 here, and then we'll end up getting a quadratic equation. So if we go to the next slide, we'll look at the simplified version of that, and I'll go over in more detail in class about how we do something like this. But you get the idea that we're multiplying both sides by that common denominator to eliminate that common denominator. Okay, so when we do that, multiply both sides by S plus 100 times S plus 100, we get 4200 times S plus 100 plus 4200S equals 13S times S plus 100. So our denominators canceled. Distribute the 4200 on the S and the 100. Okay, and then we had another 4200S, so we're combining those as well. And then this gives us 13S squared plus 1300S, because we're taking 13S times S plus 100. And we have a quadratic, right, because we have an S squared. Okay, so we're going to move everything over to one side, get 0 on one side, and we're left with 13S squared minus 7100S minus 420,000. Now we can actually factor this, but that's going to be a lot of work to try to figure out how to factor that, so we don't worry about that. We'll just go straight to quadratic formula for this. So here's our A is 13, our B is minus 7100, and our C is minus 420,000. Okay, so quadratic formula, even though we can factor this, in other words, our S will end up being an integer or something like, or at least a rational number, because we'll get an integer solution for S, or for this quadratic. We're not going to worry about that. We'll just use the quadratic formula. Okay, so plugging that in, negative B plus or minus square root of B squared minus 4 times A times C over 2A. We take the, and it's for something like this especially, do that discriminant first. First of all, if you get a negative, you'll know you have no solution, but that once we do this part, the rest is a little bit simpler. So we take the square root and we get 8,500. So we have 7,100 plus or minus 8,500 over 26. So we get two solutions when we do that. We do plus, we get S equals 600. Okay, that would be the speed going out. Okay, and then here we get a negative, minus 53.8. We skip that one, so we can just throw this one out because it's a negative. So we'll scratch that one because we're only looking at the positive. The plane's not going backwards, right? So S represents a speed. We reject the negative answer and conclude that the jet speed from New York to LA was 600 kilometers per hour, and then on the way back it's 700 kilometers per hour. So it's going faster. Remember, so S plus 100 on the way back. Okay. We'll look at these examples in class. We're going to skip similar examples in class. We're going to skip mixture problems, and we're going to skip the the interest problems for our purposes for this section. Okay, so we won't be tested on those.